okay, is a sum of even powers of rho, okay? So in the limit in which n goes to infinity, we get a n plus 2 over a of n. If I take the ratio of these two terms, then I get this goes to 2 over n. And let me call that 1 over q. Okay. Now, n is a positive integer. That means q can be either positive, n is a positive even integer, right? It's even positive integer. That means q is positive, of course, but it can be odd or even, right? Because we are dividing n by 2. Right. So now if I look at what f of rho should look like as I take the limit where, essentially for large rho, okay, so for large rho, what we should get is some constant times sum over q, and for large rho, what's going to happen is that the n will be, we can take n to be large, right? Because because the terms with higher powers of rho are going to dominate, and therefore the terms with larger number of n are going to dominate. And if I take this observation that the ratio of two consecutive terms are going to be 1 over q, we see that if I I can basically take one of these terms and factor into a smaller one, and the smaller one can be factored into a smaller one, so on and so forth. And therefore, I'm going to get a factor of q, 1 over q factorial. And then I'm going to get rho squared to the power q, because this is just rho to the power n. And this is nothing but e to the power rho squared. So thus we see that for large rho, our wave function is going to diverge exponentially. And of course, this is not physical. It's not physical because our wave function will be unnormalizable. Now, we have seen wave functions which are not normalizable. Can somebody remind me of such a wave function that is not normalizable but was physical? What about the free particle, which was e to the power minus I, say, kx plus omega t? Was this normalizable? If I take phi k squared, this is just a constant squared, right? And therefore, if I take this, this is infinity. Although this is not normalizable, but this was still physical because it did not diverge at infinity. All that is saying over here is that the probability of us finding the particle anywhere in space is equal. Okay, so even though it's not normalizable in terms of relative probability, it makes perfect sense, right? What this type of wave function is telling us is that it's just a wave function like that. And if I take a bit of space-time here, a space here, and a bit of space here, then the probability of us finding the particle here opposed to the particle here is just the ratio of this two area, right? Which is just saying that we don't know where the position of the particle is, but its momentum is fixed. But If the wave function increases exponentially, then that's completely unphysical, right? So we cannot have this. So how can we avoid this? We can avoid this if this series somehow terminates, okay? The series that we wrote down over here, this series at some point terminates. That means for some value of n, a of n is 0. If for some value of n, a of n is 0, then so suppose the value of n is 2q. It has to be an even number. That is 0. Then all the remaining are 0, right? The higher zeros. And therefore, our sum becomes a finite sum, and it cannot give me an exponential solution, which is in principle an infinite sum. Is that clear, the logic? This is the most important idea from this lecture. Okay, do you have questions? I'm willing to stop here and come back to it in the next lecture if you think it's something very tricky and I should stop here, or I can go on and discuss it more, whatever you guys want.
I think we can continue. Just
okay,
finish.
What about other people? Is it too long or?
That's all right. I don't have any problem.
Okay, so I'm just going to say that, this is going to be 0 at some point for some value of n, some even value of n, for this series to terminate, this numerator has to be 0, right? And at that value, at that point, n will be equal to 2q, because q is some positive integer. So if I do this, then the condition is that this thing is 0, and I write this over here as 4q plus 2l plus 3 equal to lambda. But now lambda is a function of the positive integer q. But remember, lambda is related to the energy. That means that the energy is a function of q as well as, of course, L. And that is given by half h bar omega 4q plus 2l plus 3. Now, if I introduce an integer big N, which is 2q plus L, and this is known as the principal quantum number, then the energy is E is given by n plus 3 half h bar omega. And this is the energy level, the discrete energy level of an isotropic harmonic oscillator. Okay. Now note that Q is 0, 1, 2, 3, dot, dot, dot. L is 0, 1, 2, dot, dot, dot. And then N then is consequently 0, 1, 2, dot, dot, dot. Okay, can I have 5 minutes of your time? Then I can just finish this off.
Yes, sir. Okay.
Okay, so what is happening? You can show, and I'm not going to show this, Q, counts the number of nodes in R, the radial wave function, okay? And so we can now look at the energy level. Suppose the principal quantum number n equals to 0. Then we have one state where Q is 0 and L is 0, okay? If Q is 0 and L is 0, because n is this, n is n is this, 2q plus L. Sorry, I should, yeah. Why do we have only one state like this? Because L is 0, right? And we know that for L0, the number of states in the angular momentum multiplet is only 1, right? Because we have 2L plus 1, right? Dimensions. So what about n equals to 1? So for n equals to 1, so we have 3 states with Q0 and L1, right? Because L is 1, so 2L plus 1 is 3. These are the spherical harmonics, remember? But for n equals to 1, yeah, this is all we have. But for n equals to 2, we have 1 state with Q1 and L0. And we have 5 states with Q0 and L2. So in total, we have 6 states. Okay. So as n increases, we get more and more states. So there is degeneracy here, right? So, E is degenerate. Energy is degenerate. And the degeneracy comes from angular momentum mostly. Well, that's where it comes from. So note that because n is related to L by 2Q, if n is even, L is even. If n is odd, L is odd. And we will see that this is related to the parity. So what is parity? Parity is how a wave function behaves under x going to minus x. And I'm just giving you information. This is outside the scope of this lecture. Of course, you can very easily show when x goes to minus x, in polar coordinates, r doesn't change. This is easy to see. And theta goes to pi minus theta, which means that cosine of theta goes to minus cosine of theta. And EIM phi goes to minus 1 to the power m EIM phi. This is a consequence of how phi behaves. Phi behaves like under parity, phi goes to phi plus pi. Okay. So if you do this, then you can show that the spherical harmonics does this. Okay. So that means that the L is, it counts the parity of YLM. But because R doesn't change, and therefore R should not change, this is what determines the parity of your wave function. And therefore we see that because L is even, and when L is even, N is even. When L is odd, N is odd. N is also counts the parity of your wave function. Okay. Okay, this parity operator, we can call it pi. And what we are saying is that, this Hamiltonian is actually commutes with the parity operator. And that means that the eigenfunctions of the Hamiltonian, which are psi ELM, if I apply the parity operator, they are eigenfunctions of the parity operator. Okay, and actually you can show that minus the sign of the parity operator is given by L, or is given by the principal quantum number n. Okay, so this concludes our analysis of the simple harmonic oscillator in 3 dimensions. However, there is another way of looking at the same system, which is in Cartesian coordinates, right? Because we could have said that H is px squared plus divided by 2m plus py squared divided by 2m plus pz squared divided by 2m. And then we could have, in fact, written the r squared as half m omega squared x squared, half m omega squared y squared, half m omega squared z squared. And then this guy and this guy gives you a harmonic oscillator. This guy and this guy gives you another harmonic oscillator. This guy and this guy gives you another harmonic oscillator. So we could have chosen, solved, treated the system as a combination of 3 independent harmonic oscillator. If that were the case, we would get the energy level to be n plus, half plus half plus half. And these halves are the 0-point energy of each harmonic oscillator times h bar omega. And then n is nx plus ny plus nz, where nx, ny, and nz are 0, 1, 2, 3. And then the energy levels would be n equals to 0 would be given by nx equals to ny equals to nz, all equals to 0, and that's just one state. N equals to 1 would be either nx or ny, nx or ny or nz would be 1. So this would give us this would give us 3 states, and n equals to 2 could be that nx is 1, ny is 1, nx is 1, nz is 1, or ny is 1, nz is 1. So that gives us 3 states. 3 states, or one of these oscillators could have 2 excitations and all the others none. So that would be another 3 states, and in total we get 6 states. Okay, so if you compare this, we get exactly the same number of states as the analysis we did here, right? Here, 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 and you see that the 2 analyses, match, and therefore they are equivalent analysis. And if you work out the wave function in one basis, you can transform into another basis by working out this transformation matrix, which is just the bracket of this guys. Okay, this is the transformation matrix, the unitary transformation matrix that transforms you from one basis to another. Okay, so sorry for the long class, but I think I'm going to stop here. And in next class, we shall start with hydrogen atom. Do we have any questions?
No.
I don't have.
Questions for this, okay?
Yeah,
The
so I don't have any
reference-
questions regarding the lecture, but I do have some issues off the record, I guess. So
Okay, maybe do you want to talk about that later tonight? Maybe.
yeah, sure.
Okay, ping me and we'll set up a time. Okay.
Okay, sir.
Anyone else? Okay, so thank you very much. Sorry again for the long class. I guess Wajiha was here at some point. So the only person absent today is basically Rahul, and who else? And Nahi. Okay.